Have you ever wondered how quantum computing differs from the classical computing we use every day? Welcome to our exploration into the fascinating world of computing, where we'll be taking a deep dive into two distinctive types of computing paradigms: classical computing and quantum computing. Classical computing is something we're all familiar with. It's the backbone of all the devices we use daily. But there's a new kid on the block: quantum computing, promising to revolutionize the way we process information. In this video, we'll explore the mechanics of both classical computing and quantum computing, discussing how they work, their applications, and their respective advantages and limitations. We'll delve into the world of bits and binary systems, then journey into the realm of qubits, superposition, and entanglement. As we uncover the potential of these technologies, we'll also grapple with the challenges they face. So let's dive right in and start by understanding what classical computing is. Classical computing, the backbone of all our digital devices, operates on a binary system. At its core, classical computing is all about manipulating bits, the fundamental units of information. Each bit can be in one of two states, 0 or 1, much like a switch that can be either off or on. This binary system is the language of electronic devices, from the smartphone in your pocket to the most powerful supercomputers. Whether you're sending a text, browsing the internet, or calculating a spreadsheet, you're relying on a series of bits flipping between zeros and ones. In essence, classical computing is a series of these binary decisions, creating complex algorithms and operations from simple two-state bits. It's a proven, reliable technology that underpins virtually all our digital interactions. While classical computing has served us well for decades, the advent of quantum computing promises to revolutionize the field. Quantum computing, a relatively new and exciting field, operates on principles of quantum mechanics. Dissimilar to traditional PCs that utilization bits, quantum PCs use quantum bits, or qubits. You see, while a classical bit can be either a 1 or a 0, a qubit can be both at the same time thanks to a property called superposition. Imagine a coin spinning in the air. It's not just heads or tails, but both until it lands. Another fascinating principle integral to quantum computing is entanglement. Picture two entangled qubits as a pair of dice. No matter how far apart they are, if one shows a 6, the other will too, instantly. This spooky correlation enables quantum computers to process vast amounts of information simultaneously. These unique properties make quantum computers incredibly powerful. They have the potential to revolutionize fields that rely on crunching large sets of data or solving complex problems. Cryptography, for example, could be transformed. Whereas classical computers would take an age to crack a cryptographic code, a quantum computer could do it in a snap. Quantum computers could also tackle problems that are currently too complex for classical computers, like simulating molecular behavior for drug development or optimizing financial portfolios in real time. With such potential, why aren't we all using quantum computers already? Both classical and quantum computing have their own set of advantages and limitations. Let's begin with classical computing. Its reliability is a major strength. We've been using and fine-tuning these systems for over half a century, so they're trusted and understood. When you send an email, stream a movie, or even launch a rocket into space, you're witnessing the reliability of classical computing in action. Efficiency is another advantage. For many everyday tasks, classical computers are highly efficient. They're adept at handling the operations we perform daily, from browsing the web to crunching numbers in a spreadsheet. Lastly, classical computing's widespread use and accessibility cannot be overstated. From the smartphone in your pocket to the servers that power the internet, classical computing is everywhere. It's a technology that's accessible to millions, shaping our world in countless ways. But classical computing isn't without its limitations. When it comes to large data sets and complex problems, these machines begin to struggle. They process information sequentially bit by bit, which can become a bottleneck when tackling problems that require a vast amount of computational power. Now let's shift gears to quantum computing. Speed and efficiency in processing complex calculations is where quantum computers truly shine. Thanks to the principles of superposition and entanglement, they can process vast amounts of data simultaneously. This gives them the potential to outperform classical computers in certain tasks by several orders of magnitude. And it's not just about speed. Quantum computing could enable breakthroughs in fields as diverse as medicine, finance, and cryptography. Imagine creating new drugs by simulating molecular structures, or cracking cryptographic codes that are currently unbreakable. The potential is enormous. However, quantum computing is not without its challenges. For starters, it's a technology still in its infancy. We are yet to fully understand or harness its capabilities. Cost is another issue. Building a quantum computer is an expensive endeavor, well beyond the reach of most organizations. And even if you could afford one, you'd need a specialized environment to operate it, given their sensitivity to changes in temperature and electromagnetic interference. Finally, there's the issue of error correction. Quantum systems are notoriously error-prone, and developing effective error correction methods is one of the biggest challenges facing the field. As we can see, both classical and quantum computing have their strengths and weaknesses. So where does this leave us in the grand scheme of things? Let's take a quick rewind. We've delved into the intricate world of classical computing, exploring its backbone, the binary system and bits. It's the established, reliable technology that powers the devices we use every day, from smartphones to traffic lights. Then, we ventured into the quantum realm, a frontier of computing that's as fascinating as it is complex. Quantum computing, with its qubits, superposition, and entanglement, promises to revolutionize how we solve problems. It could potentially unlock new heights in fields like cryptography and complex problem-solving. However, both have their strengths and their Achilles heels. Classical computing, while widespread and accessible, struggles with large data sets and intricate problems. Quantum computing, despite its potential, grapples with technological limitations, cost factors, and the need for specialized environments. The chessboard is set, the pieces are moving. We're living in an era where classical and quantum computing coexist, each carving its own niche, each shaping the future in its unique way. As we stand at this crossroads of technology, let's ponder. What's next? How will these two computing paradigms shape our world? It's an exciting time to be alive, to witness this dance of technology, this symphony of bits and qubits. Which computing paradigm do you think will dominate the future? We're eager to hear your thoughts. Share your opinions in the comments.